Okay, so I think let's begin. Right. So in last lecture, we talked about the overview of this course, and we basically stopped in this slide about the history of networking. And today we will continue with this. So, and we will also move to the next one. I think there's a chat. Yeah. Good afternoon, everyone. Okay. Let me. So last time we talked about the Morse code, right? And then we stopped right here at the telephony. Okay. And we talked about why the regular way of design is not a good idea, because, for example, if you have people you want to call each other, right? So you can have a dedicated line, right? So for example, you can connect everyone with everyone else, okay? But as we explained, that will generate so many connections and square amount of connections, which is really not affordable, okay? And the current solution is really using the so-called trunk lines, which means you have some hubs, right? So, and you are connecting to your local hub, okay? And then these hubs will form a more densely connected network, which will connect each other. So for example, when let's say this guy is A, okay, I want to call B. So they will establish connection through this link here, okay, right? And in the meanwhile, if, for example, here we have another guy from the same building, for example, C want to connect to D and talk to D, we can also do that through this link, right? So we don't need every pair with each other, okay? But of course, the bandwidth here will be a little bit high, right? So, and for example, if I have an E who want to talk to F, right? So, of course, here we have to occupy this line, right? If this bandwidth here is equivalent to two lines, then A and E can both connect to B and F, okay? But what if, let's say I have a C also finish this call with D, and I want to call to G, for example, here, right? But the bandwidth can only accommodate two calls, for example. Then we cannot do that, right? So these two should have much higher bandwidth than the other, the end connections, okay? And in the
Can you repeat that part again? The
yeah,
you say you can connect to, so you can't connect to two phones, to two
yes,
truck line.
yeah. So for example, this is trunk line, right? So let's say the bandwidth is 2C, okay, right? And this guy want to call this guy, let's say this guy, and they want to this guy. They can establish a C, 2C, and a C, okay? And this one, let's say this guy want to call this guy, right? So they have another C, and they occupy this and this C, right? So in that case, this guy, if, let's say this person want to call this person, then they cannot do that, right? So there's some resource limitation here, okay? Because we don't want to connect so many lines. So basically, we are assuming that not many people will simultaneously talk from one spot to the other, right? If everybody is talking to everybody else, then we do need the fully connected structure, right? The complete graph structure, okay? So we are assuming that not everyone is using all the service all together, okay? Do I answer your question?
Yes, I believe so. So like you can't use, so they can't, all three can't connect to each other, can't connect to the same truck line, but two of them can, like four of them, two of each side can, but not three of them.
Yeah, because the bandwidth uh, may be a little bit low, right? So because otherwise you are basically having those physical lines. Sorry, let me go back. Otherwise, you are basically having the physical lines, connecting. Let me change your color. Okay, so this is like you have a line here, and then you have a line here, right? So this is more like a switch, okay, in between. Right? I will switch you to here, switch you, but I only have two bandwidths. I don't have three, right? So internally, we have this kind of switching mechanism, right? So for example, let's say we have two locations connecting, right? So you can consider these are the walls like this, right? So these are the ABC, okay? ABC, right? So I have ABC here, okay? And I also have DEF here, okay? DEF. So I have DEF here with another one, okay? DEF. And in that case, basically this guy is doing something like switching, right? So if A want to talk to D, I will make this connection, right? So then this signal is kind of connected, okay? And B want to talk to E, I will make this connection, okay? But you cannot, for example, if C wants to call D, then it will not be passing through, because if C also talk, then this channel is kind of, interfere, right? So basically the switch makes sure only one row and one column, like each row and each column only have one connection. That's it. But if you have everybody want to talk to everybody else, right? So maybe this is not a complete connection like this, right? Maybe there's a bandwidth, how many it can support internally, okay? Right, so then you cannot do too many. Okay, so we are assuming that, let's say, from your building to the other building, even though there are many residents, right? Not all of them are occupying all the phone all the time. Otherwise, the results will, you still need a full connection. Okay. And so this is basically, yeah. So this is basically the idea. So because you don't call everybody else, everybody is not calling everybody else all the time. So we can reduce the results a little bit, but we allow some like trunk lines to be shared. Right? And multiplexing basically is saying, hey, when the signal comes to here, which client you want to go to, right? If A is calling B, I should not multiplex to C, okay? So the advantage is that, it's easy to use, right? So the complexity is low. It's not n squared, right? So it's much lower than n squared, right? So, and the cable management also tractable, because if you have 1 million cables, right? So you think about the fault rate, right? It's very high. You kind of every few minutes you are replacing a cable, right? So replacing 40 cable, okay? But the problem is that you need to, just like what we said, those rows and columns, you need to connect them, right? So this is a manual switching. Right? It's very slow, especially think about, there's a human behind the board, right? So this will take 15 minutes to set up if you have cross-country call, right? Okay, so any questions? Right, let's continue.
Yes, can you repeat that? I didn't understand what you were saying.
Which part you don't understand?
The last slide, that one.
Oh, the last one, right? So this one. Let me show an image. Maybe that's better. Actually, I think we have an image last time. Let me put here. Yeah, so you need a human to do this. Okay, so that's very slow. I'm talking about the old days. Okay, now we don't need it. Okay, I'm talking about this is the history, right? So I'm talking about this time. Okay, this like way last century, for example. Maybe that's confusing. Do you answer your question?
Yeah, that answered the question.
Okay, yeah. So the last century they are doing this, right? So this is super slow. Okay, so no, of course this is not now. Okay, so we are talking about networks, right? Data link. We are not talking about the voice link anymore. Okay. All right. So this is now coming forward. We have some key, milestones here in different time. I think I will leave it to you to read, right? So for telephone lines, when you connect a telephone, you will use a twisted pair if you ever do that, right? So you have by a telephone, you have one port on one end and another port on maybe on the wall because there's a port that that is set up there, right? So and this is for local, means that you connect. Let me see. Maybe we can use image that will be better. Okay. Image. Yeah, my network is a little bit slow somehow. Okay, so twisted pair phone. Okay, so you typically will do something like you will connect this kind of pad, right? One end is a phone, the other and often the wall, right? You have a port there. Okay, there's a like kind of like this kind of structure. Okay. And then, this is for local loop, because, at the backend, when it gets out of your building, right, it's a different story, right? There's a backbone network, okay? And then AT&T is formed in 1885, right? So AT&T has was growing very quickly at that time. There's even, the AT&T lab, right, the Bell Lab. They have a lot of, I think, Nobel Prize winners, right? Until recently, because, the computer network has been so dominating, right? So they sell this to Nokia, I think, right? So and by that time, you can see the motivation, because people are still using switching board, right? So that's kind of crazy, okay? And there's an automatic telephone switch. You no longer need a human. Of course, it will be also much faster, right? In 1892, okay. In 1903, in the United States, there has already been 3 million telephones, okay? And there's some milestone like long cable connections, right, between different continents and even across the ocean. Right? And then, finally, there's a national numbering plan, because there are so many phones, right? So we need to have the phone number for each person, right? And we should have, basically, this is the same also for IP address if you look at the internet right now, okay? So you have the different segment of code, right? So, for example, for country, you have 1 and the 205 is, for example, for Alabama, right? And then you have some region, like county, etc., some other numbers, okay? So this is an organization by geographics, right? So like United States is all with 1, right? So for some other places, maybe with some other numbers, okay, right? And this is then by the state, right? So maybe some state have multiple code, of course, right? So and then this may be for the county, So this is also the same for IP address. Actually, if you look at the United States and the UK, it will be different address in the beginning. We will talk about it later. And all UAB maybe share the first segment of so-called subnet. Okay, so IP address, the first segment is very similar. And then we have the first use of a model for machine-to-machine communication to computers. Now we are talking about computers. Okay, and the tricky thing is now, unlike voice signals, which are analog signals, right? So for computer signals, it's actually digital signals. Okay, so you need to transform this analog signal to 0 and 1, right? So like the signal is on and off, and beyond certain threshold, it becomes 1, and below certain threshold, it becomes 0, right? But we are not touching that stuff at the physical layer, okay, because this is really lower level, okay? We will briefly talk about it in one of the chapter with maybe 10 slides, okay? And then we will move quickly to the link layer, where we already have the digital signal and how we handle the rest. And yeah, any questions so far? Okay, now for computer networks, we have a few, different types, okay? So one type is called a LAN, okay, local area network, right? This is local network, okay? For example, if you go to our computer rooms right now because of the pandemic, right? So if you later, the pandemic's over, if you go to the labs in our computer rooms, okay, that room is connected by local area network, okay? So you cannot connect from outside into this local area network, okay? So each computer will be assigned a IP address, okay? Just like phone number, right? IP address of its own locally, okay? It's not globally unique, right? Because maybe for cross a building to another department, because we are computer science department, right? Maybe to ECE departments, they have, the same IP address. That's fine because it's just local. And there's also global, right? So the wide area network. This is really, we're talking about internet, right? So you have those subnets that are connected with each other. And then you should have a public IP address, uniquely determining who you are, right? Later, we will talk about another, technology called the NAT, right? So NAT, okay? So that basically is an interface, right? Here you have an IP address, public IP address, but you have many local machines, okay? Outside cannot see your local machine internally. Right, so you only pay one IP address because the IP address you need to pay this, the service provider, right? So you can use multiple devices with one IP address. This is also what's happening maybe in your home device, right? So you can have phone, you have iPad, You can have other stuff like TV connected, but you are only using one IP address. And each local device actually has its own local IP address in your local area network. Okay, so we will cover these things later. And they're also like, so right now we mainly using public network, right? So because we want to connect with each other, and the internet is the backbone. Okay, whenever you have access point to the internet, then you can visit everyone else. Everyone else can visit at least to your IP address, this level. Okay, right? And so this basically says you are connecting to the public network, right? But there are some important networks you want to keep confidential. For example, the military network, right? And some others, maybe you don't have connection to the backbone internet. For example, if you are in a very less populated area, there's no base station, right? And you have some sensors like a sensor mode and or some other drone device, right? They may be, the closest internet call may be many miles away, right? So you will communicate with each other in a more like a private, let's say, drone network, and take like images, etc., right? Take pictures. And when you fly back to a nearby base station, you can upload these things. Okay. And so there's also like special purpose, networks, like for credit cards, right? So the bank system, they have their own network. Okay. So, and finally, so there are different technologies. Okay. So these things actually, we'll talk about different networks, but they actually belong to different layers. We will look at them in more detail later. So for now, just keep in mind what they are, right? So satellite is really for like a rural area or tribal area where we don't have let's say you have base stations, right? You can connect the internet, but there's let's say there's a tribe here, right? So there's no infrastructure close to this tribe, right? So you don't have any base tower you can connect 4G. Okay, so in that case, you need to get help from a satellite over the sky, right? So they will connect this and then send stuff to you, and you can send to satellite and send to the base station, and then you access every backbone network using routers. Okay, so this will be relatively slow. I mean, the latency will be long. Let's say, hey, you say hi, maybe after 2 seconds, another guy will say, hey, hi, because it's long distance, right? Compared with if you are directly close to access point. Okay, but you don't have to deploy infrastructure. So this is often a solution if you are far from the network infrastructure. Okay, and the copper is really like the dominating technology these days. Like if you connect your like if you connect to the internet using the cable modem that you also share with your television, right? So in that case, it's actually a cable. So it's like a wire where you have metal here, you have then one needle in the middle. Right? So these are the maybe plastic, I don't know. Right? So this kind of thing connect to some like a port on the wall and for television, but you will also connect to a modem, which will kind of also allow you to share this link out, okay, to the backbone internet with your maybe wireless router. Okay, and fiber is really something used in the backbone or even over the ocean, right? So from Asia to like North America, right? So there's fiber connections. The reason we need fiber is really because it's it's transmitting by light. It's very fast, okay, and it's straight in some sense. There's some magnifier because it's so long, the light signal will be weakened. But overall, it's really fast, okay? So, and it's very high bandwidth, right? So you think about if a lot of people here in North America and talking a lot of people in Asia, right? So you do need the bandwidth here is very high compared with individual bandwidths here, okay, inside. This is similar to what we talked about, in the telephone slide, okay? Any questions so far?
Hey, Professor, I don't mean to interrupt you, but your connection for a lot of us is kind of cutting in and out, and we're having a hard time hearing you.
Oh, really? Okay.
Yes, sir.
Yeah, my connection today is a little bit not so good, but let me see. Oh, I think I'm not taking the video also, right? Let me pause. Okay, I'm taking the, so I think I will also share the video with everyone. So later you can also rewatch on YouTube because my internet connection may not be so good today. Yeah, so just let me know if you didn't hear something clearly. I will repeat that. It's okay?
Okay.
Yeah.
All right.
Mm-hmm. Yeah, finally, we have the concept of circuit and the packet switch. Okay, what does that mean? So you think about if you are calling somebody A, calling B using phone, okay? Then you should have a circuit connecting them. Maybe there's some switch in between, but finally, all these lines are occupied by you only. Okay, you cannot occupy something else, right? If you have somebody else, C, talking also on this line, then the voice are interfere with each other. Okay, and that's not okay, right? So in that case, circuit switching is really very low efficiency solution, right? Because whenever you establish a communication with other people, you have to occupy it until you hang up your phone, right? So then disconnect it. Okay, then this link may be used between C and D. Okay, otherwise this link will be totally occupied. So now, so this will not work out in the internet technology these days, right? So you see the data bandwidths are like a megabyte per second, even on the internet from one end to the other, right? Or even higher. Okay, so we are actually, for the backbone internet, we are using packet switching. This is another idea that's very smart. You think about, for example, we have two routers, okay? Let's simplify the problem. We have two routers connected, and let's say two buildings, okay? From, let's say, me to your building, okay? So we have A, B, C, three people, okay? Send stuff to D, E, F to the other side, okay? So the bandwidth may be, let's assume 3 megabits per second, okay? Mbps, right? And now, actually, if let's say you are Skyping the other party, right? 1 MB per second, mbit per second is enough, okay? So this is a megabit per second. In network, we usually use bits instead of byte, okay? Because we are thinking it's a bits that are sending through. So in that case, frankly speaking, all you need is something like this, right? So you can talk to this guy using 1 megabit per second, and this to here using 1 megabit per second. And this C talking to F also using 1 megabit per second. And previously, this is not allowed if you use circuit switching, right? Because this line here can only be occupied by one person, okay? One connection and one pair of people, okay? And now, because we use packet switching, we allow 3 of them share as long as their total bandwidth, 1 plus 1 plus 1, right, is about 3, right? Then they can talk together simultaneously. So the idea is very simple. You think about what they do is you encode their voice into small packages, right? So packets, okay? So they have small packets here, right? And it's really, the router is just keeping the packet, store the packet and then forward it. And then at here, it will deplex to the destination, okay? And then it's possible that, for example, on this wall, this packet is from A, okay? And then in another time, maybe the next packet is from B, okay? And another time, maybe another packet is from C, okay? And then another packet may be from A again, right? And we don't need that frequency because, the speed and the frequency are really high in this line, right? So, but as long as you have some frequency, you can hear the other guy's voice clearly, right? So I just need every 1/3 of the frequency to encode the voice, right? So this is the same idea as if you are moving your mouse, right? So if you are moving your mouse and you only have one CPU, that's fine, your operating system is still running, right? So this is time sharing because capturing your mouse movement only needs very, very little cycles, maybe 1 in 1 billion cycles to react to your mouse movement. Right? The other cycles of the CPU can be used for other purpose, okay? So this is a similar idea, but actually this goes beyond that, right? So, the backbone does not just have 2 endpoints of routers, right? We have many, many routers, which means maybe there's another traffic here. They can also share the router link, okay? You don't have to share it dedicatedly. But there's a problem here. For example, what if I'm playing games, right? I need 2 megabit per second, right? For example, in that case, your total required the total sending packets is 4, right? 2 plus 1 plus 1. And this link can only hold 3, okay? That's where it will cause a problem, because this router can only send things in 3 megabits per second, but you have total 4 megabits per second coming in, right? And that's how this congestion, and we do congestion control, and these things we will tell you later. Okay, so as the class unfolds. Okay, so basically there are different ways. One is to say, hey, you should, for example, you should back off, right? You should just send in 1 megabits per second, even though the service quality rate will be low. Okay, another way is possible that you will lose some signals, right? It will drop some of the packets here. Like we drop this because we don't have the buffer size to hold so many packets. Okay, so this is just a very brief idea of circuit and packet switch. Right. Again, here we are just giving you a very high level idea. We will repeat all those stuff again later in this class. Yeah. So let's continue. Then then we move fast on to the history of the internet. Okay, internet is really the wide area network, right? So, and initially it's actually not a wide area network. It's a lot of subnets, right? Starting from you know, Department of Defense, there's the ARPA, right? Research Institute. There's the ARPANET, which is like the previous network before internet. Okay, so, and it's actually, you know, initially the packet switch network, the idea is formed in MIT. A lot of people here are actually very big guys, right? So you need to remember, I think 2 people like Robert and Vincent, right? So they are actually getting the Turing Award for inventing the TCP, okay, the TCP protocol. We will also describe those things later, okay? Right, so, and here, so there's a few milestones, but I will leave it to you. But what you need to know is, for example, you can connect the computer to the phone line, right? Initially, how do you don't have that infrastructure, right? Backbone. So initially, you want to connect out to your house, right? So you will use a phone line or you use a cable of your television, okay? And you connect them out, right? And this technology was very early, okay? And then Robert published a version of ARPANET, and ARPANET then unfolded and developed, and the first demonstration is here, right? By that time, ARPANET is not using TCP protocol. I bet you know, at least you heard of TCP IP, right? TCP is a kind of protocol in the transport layer. The purpose is to do end-to-end communication for your apps. For example, you can establish a TCP link from this machine to that machine, and then send stuff, okay? And the important thing about TCP connection is that, for example, if A and B do the connection here, right? And A send, let's say, A, B, C, right? And then send D, E, F, okay? It guarantees that A, B, C, and D, E, F will be received in the order it's sent. For example, if you first send D, E, F, and then A, B, C, B will always first receive D, E, F, and then A, B, C. This is in order sending, right, in TCP. If you use UDP, there's no such guarantee, right? And if you, but there's no guarantee because maybe through the router, the later packet will arrive early. So there are some tricks that is handled by TCP to guarantee that, right? So, and also IP protocol is in the level down, okay, in the network layer, okay? But early on, and there's also congestion control we'll describe later, okay? Early on, we don't have TCP, right? The first version with ARPANET is NCP, okay? The network control protocol, right? And later, after, you know, Robert and Vincent, right? So Robert, Carl, and Vincent invent TCP, okay? There's a internet switching day that everybody has to switch from NCP to TCP. We will see that milestone later, okay? So these are the key milestones you need to understand. So the other stuff are not so important. You know that the network, actually a lot of people come initially from MIT, initially this internet, and also from those UCLA, right? So this is actually a router kind of stuff, early version of a router, okay? And why do we do packet switching? Because of the so much preparation, I think now it's pretty clear, right? So if you use a telephone network, the circuit switched method, right? We establish a dedicated circuit between 2 pairs of communication, right? 2 parties of communication. then we need to reserve this call end to end. All these lines between those switches from like maybe East Coast to West Coast, these lines are occupied. Nobody else can use it, okay? And it provides very good quality of service because you can listen to every detail, even background noise of the other party, because the whole while is yours, okay? But the problem is that it's a result intensive, right? It's not efficient, okay? And a lot of the results cannot be reused, right, in parallel, okay? And there's also, maybe security issues, right? So maybe people can eavesdrop your communication, okay? And the design is also very complicated. We haven't touched the automatic switching part, right? So you can see it's like a mechanical structure that needs a lot of design and connect to different geographic locations, okay? On the other hand, packet switching just get rid of all those complications, okay? It's like a sweet point, right? So there's no connection state, right? The network is store and forward, as we said. Router does not care about who is sending to who, okay? If a package is sent to a router, I just check the IP address of the destination, decide where I should get to the next router, okay? That's all it does. From the incoming channel, I get a package, and then I look up my IP table. I will talk about the IP table later, okay? And then I forward it to the corresponding outgoing link, okay? So that's all it's doing. If I don't have enough capacity, I will drop some packets, or I tell the sender, hey, you should back off, right? Don't send so fast, right? So there's really no connection state necessary, right? Everyone is sharing the router and the links, okay? And there's a minimal network assumptions, right? You don't need so complex designs because now it's very simple. It's a package and then I store and forward, right? It's a public, like a service provider, right? So you don't really care about this is internet service provider. You don't care about who is connecting to who, okay? And so there's a lot higher utilization ratio using the statistical multiplexing technology, okay? So now, on each link, you can have different connections, different data links between different pair of people, right, sending together. Okay, any questions here? So we are really emphasizing the difference between packet switching and circuit switching, right? Packet switching is what we are using here. And this is very important. You need to understand the idea of packet switching. Okay. And we will discuss like router, all those things later. Okay, but again, so this is the first step. You get into a high-level idea, and then we can unfold this other stuff. Okay. So here is the ARPANET, right? So ARPANET initially in 1969, there are only 4 nodes, right? So in UC Santa Barbara, UCLA, Utah, and yeah, anyway, so there are 4 nodes, okay. And so later it goes a little bit larger. You can see a lot of them are campus, right? All with ARPA. Okay, so this is the Department of Defense Research Institute. And you can see here, most of the institutions are like on the close to the West Coast, right? So on the West, okay, these are on the East, right? So and this is 1971, okay? So, and in the middle, there are very few links, but because of the links, they are still connected, right? So you can send stuff from MIT to UCLA, for example, right? But by that time, it's not yet internet, it's ARPANET, right? So because we don't have everyone connected, okay? And here's an ARPA network structure, right? So this IMP, as I said, is and the TIP are early versions of router, which now it may not be so important for us. So we will just briefly discuss it, okay? So there's also like some side connections, right? So like to Hawaii, I think so you can connect out. Okay, so and early networks actually start from individual subnetworks. Okay, for example, maybe California, they have their own network. On the West Coast, on the East Coast, they have one. Right, some other places like NSF, they have one. Okay, DAPA, they have another. Right, so they are all isolated networks. Right, so they are just a bunch of maybe switch or routers connecting a bunch of machines in their local regions. Okay, And so of course you cannot communicate with each other in that case, right? I think these are switches. And then Robert Kahns proposed some ground rules, right? So it's a vision about how to design the ARPANET, which later becomes the internet, right? So this lays a foundation of these ground rules. Okay. Before I enter this, any questions? If you have any questions, just feel free to ask. Okay. If not, I will continue. Right. So initially, each network is independent, right? So you cannot force them to change. For example, if the subnet, let's say in California, you cannot force them to change it if you are in MIT, right? So there's no global control. Okay, you don't have control over others, right? So this is also the same now, right? So you can only build a firewall to filter out some traffics, right? You cannot prevent other people to connect to the internet, even maliciously. And so there's no global control. Everyone is autonomous in some sense, right? Every subnet is autonomous. And so this is the best effort communication. There's no guarantee because you think about it, you can send in very high speed, right? Through the network. And but the intermediate link between routers may not be able to send all these stuff to the destination because of the bandwidth limit. Okay, in that case, the router has to drop some packets, or it has to tell you, hey, slow down. But you may not need to listen to it, right? TCP protocol is one that allows congestion control. So you will, if you follow TCP protocol, you will back off your sending speed, okay? Because that makes no sense. It's just cause congestion and packet loss, right? And so this is the best effort communication, right? Because it's all public service, right? It's not a dedicated line, right? And it uses routers to connect different networks, okay? And these ideas are later bring about the IP protocol, right? So the IP, everyone now is using IP address, right? This IP address is like the telephone number, right? In early days, okay? So even now, right? So everyone have a unique IP address, right? When you connect out of your apartment, okay? And this whole structure leads to the internet as we know it. IP protocol is basically telling you how to route packages between routers to the destination, right? And so on top we have the transport layer and the application layer. But down we have the link layer and the physical layer, right? And actually, in the network layer, we only have IP right now. And also we are trying to switch from IPv4 to IPv6 because IPv4 has two limited IP addresses, okay? Because the length of the IP address segment is too few, right? So we have 6 billion to 7 billion people in the world. It's not enough. So we are transitioning to IPv6, but it's a very difficult process because this is the bottleneck, right? No matter how many layers they are sharing the network layer, which is IPv4, okay? And so all these ideas actually lead to the design of the internet as we know, okay? And the internet is still structured in this way. Still on Kahn's ground rules, okay? These are early on when he proposed for the ARPANET. That's the vision. We are still implementing this vision. Okay, so here is the illustration, right? So previously, every different institutes or regions have their own subnet, right? Then we are connecting them using routers, right? And then those routers are like an internet service provider, so you need to build this, right? And then you pay the service provider to get connected to the backbone. And here's a visualization. It may not make too much sense, but we can see how it grows. Right? In 2000, we have a lot of connections, the router and the endpoints connection like this. And then in 2006, we grow really quickly, and then 2009, and so we can see that more and more people are connecting to the internet. And again, yes. So if you remember, like big guys in the area, Vincent Cerf and Robert Kahn, right? So they're inventor of the TCP. Okay, so that's a big deal because before that, people are using NCP, and so there's a flag day basically saying that because those subnets are connected together, right? And they want to switch from NCP or their own protocol to TCP, right? So there's a flag day saying, hey, you all should switch to, let's say, TCP. You should stop using this protocol, right? Because if one end is still using the old protocol, the other is using the new protocol, they cannot communicate, okay? So there's a flag day back in 1983. That's a very interesting history, right? But now it's really difficult. You can see that we need a lot of like tunneling technology to switch from IPv4 to IPv6. It will be a long process because we have so many people using internet nowadays, unlike the old days, right? There's only a few institutions, okay? So there's no way to switch one day just to another protocol at the IP level at least. Yeah, and you can see here's a lot of history, right? And another interesting stuff is here. So there's an internet meltdown, right, due to congestion because more and more people are using it. So there's a, there's a problem, right? So the router basically keeps dropping the packets. Okay, there's nothing sent, right? So the reason is, as we said, very simple, right? Because if you have a router, but you see people sending like crazy, right, to you, okay, but your outgoing bandwidth is not so high, right? Then you will drop packets, okay? And once you drop packets, right, so then the sending will not be successful. This sender will resend. And then it's a deadlock, right? It's a infinite loop, okay? And you never get anything sent to the other side. So this is causing a lot of problem back then, okay? And then von Jacobson actually improved the TCP protocol. Previously, they do not have congestion control. Now, by that time in 1986, Van Jacobson basically improved the TCP using a new component that if you're sending something, initially you should send with the speed, the bandwidth increasing linearly. Okay, but what if you finally detect, hey, there's congestion, right? So congestion means there's no acknowledgement back because you never get your package out to the other part, right? If that's the case, and you find that after some timeout, you still don't get any response, you should back off. When you back off, you actually do exponential backup, right? You cut by half, okay? You think about it, everyone is trying to increase slowly, and suddenly they find that there's a spot that you kind of cannot fully utilize the bandwidth, right? You start to have some package loss, okay? And then you will back off to half. And this guy will also back to half. This person will also back off to half, right? So if everyone follow this rule, actually we will be able to utilize a significant portion of the bandwidth on this line, right? Because if you find it as congestion, you will not keep sending and cause drop on your own packet and also other people's packets, right? Everyone is politely backing up. Right? By adding this, actually the backbone internet is back into work. Okay, so we will talk about TCP congestion control later. Okay, so this is something else that is interesting. Okay, and then there's some old network like FSNet that merge the ties. Okay, that is metal. So and there's also some invention of multicast, and we will talk about what is multicast later. Basically, you want to send, it's like a radio, right? You send something to multiple people, right? So if you all tune to that channel, you can listen to it, right? Okay. So and there's a the internet bubble around 2000, okay? And a lot of companies actually died. And then in this century, actually, there's a lot of internet companies that boomed, right? So the Facebook, Google, all these, right? And so here's a development of the applications, right? So in early days, we actually already have the email, right? So the email SMTP protocol, right? So email has its own application of protocol, right? Okay, we will reach that later. Okay. And I'm not sure how many of you have to use a telnet. I think now almost everyone using SSH, right? Secure shell. But early on, like you do use telnet to do remote connection, right? So to the other machines, okay? And the DNS is when, we have so many IP addresses, right? But we don't really want to remember these IP addresses. They have no meaning, right? For example, if you type google.com, it's to Google keyword search, right? Google's website, right? If you go to uab.edu, we are going to uab.edu. But you think about the servers, right? So in Google, for example, UAB website, okay? It's actually just the, IP address, one IP address, right? So you don't really want to use IP address to directly access because you cannot remember it, and there's so many IP addresses. But there are meaningful domain names. DN is domain name, right? So, so this is domain name service. Okay, so there's some globally there are like tens of domain name servers. Okay, help you when you have the domain name, you will send a request to those servers, and those servers will help you translate the IP address back. Okay, and if you are creating a new domain, let's say you register a new website, you want to create a new domain, you're paying them to enter your domain name and IP address mapping to their service. Okay, and of course there are not too many of those service providers. Most of the service providers you are connecting to maybe a secondary agent for them, right? So, and this is a backbone domain map to IP address transfer. Okay, and it's like a phone book, right? So you look up the name of the company you want to go, and you get its phone number. But these are actually in global service, and you don't actually go to those domain servers again, right? Otherwise, they will get traffic from everywhere, right? So you also have local cache, right? So local service provider have local cache of those tables, okay? But that also means that if you change your domain name and IP address mapping, it will take maybe half a day to propagate this information to like flush out the old cache, outdated cache worldwide, right? So it's a safer way if you wait for half a day or even 1 day to see your website online and be able to be visited by everyone in the world. Okay. So this domain name service, and FTP is a remote file access. Right? So I think everyone used it. Right? So you can pull your file into a server, and you can also pull out from the FTP window to your local. Okay. So all these actually have their own protocol or their own device. Okay. So again, we are talking about applications. Right? So these are application layer stuff, right? Even above the TCP. Okay, some are using TCP, some are using UDP. Okay, and there's also a network file system, remote file system, right? So when is NFS useful, right? So this is, for example, if you, I'm not sure whether you use the department server, right? Wherever you connect to, let's say we have 3 different servers that you're using, but they all are mounted to the same folder, right? So same. Let's say your dash home and dash your name, right? Your username. Okay, this is the same space, right? So that's kind of weird because each machine should have its own disk, right? Why everyone is accessing the same disk, right? So if you put some file and your home, right, and the other server when you log out, you can see this file, right? So this is because this disk is mounted to all these servers. This is basically a network file system. Okay, this is a disk connected by NFS. Okay, so this is how this is treated. Of course, you can also have your local disk mounted. In that case, other people cannot visit. Only you can visit your local disk, right? And then we have the World Wide Web. This is basically HTML, CSS, those technologies. But basically, you want your browser, like you want to make some website. And you wanted the browser to interpret into visual-friendly websites, right? And by that time, this is really early days. You only have the static website, right? So later we have Web 2.0, which means also we have HTML5, right? So basically basically there's programs, there's server program like a JSP server or .NET server, PHP server. They can translate the program and write the response website according to your input. Right? If you are purchasing stuff in Amazon, it need to get something from the database and then show them on the website, and then compose the website and then put it in the request and send back. Right? So this is Web 2.0. Okay. Let me see the time. Yeah, I think that's pretty much for today, right? So our time is up. Okay. Yeah, if you have any question, feel free to ask. Right. So otherwise, I will wait for 1 minute and then I will disconnect. Thank you.
This will be posted. The video, it won't be posted on Canvas. It'll be posted on YouTube.
Yeah, I'm posting it on YouTube, right? Because it's easier for everyone. Just click and you can watch. Oh, you
Okay.
prefer to use cameras because YouTube is easier, right?
Yeah. So like, I just want to be able to access it because it was kind of choppy sometimes. So I want to go back and access the video. So how do we get to it? Is on the syllabus?
Oh, It's actually, I'm standing through Canvas announcement. Let me show you. Okay, so if you go to Canvas, and you see course. So basically, whenever a video is finishing uploading to YouTube, I will send an announcement through here. And these announcements, by default, it should go to your email address, okay, UAB email, right? So like this, okay, and then you can watch it here, or you can just go to the YouTube link and watch on YouTube. It's okay.
So yeah, thank you.
Yeah, you're welcome. And if you don't get it from your email, just let me know, okay? Because it should go to your email. Every announcement from Canvas should go to your email. If not, you need to figure out with IT support, right? Ask IT.
Okay, I will.
Okay, thank you. Yeah, for the first quiz, we will post it maybe next week, okay? Because the next slide will be relevant to the quiz. Okay, so today basically we are basically almost finishing this slide, but we only have maybe 3 more pages. Okay, and the next week we will finish the architecture chapter, and then we will have a quiz for you to finish in 1 week.
Are we going to be doing a lot of problem solving in this class, or is it mostly just memorization of a whole bunch of different concepts?
There are 2 components. One is concept. Another, just 3 components. One is concept. Another is play with, Cisco package tracers. This is for labs. Starting from next Friday, we will have labs, right? So that's a stimulator for Cisco devices, right? And when you actually buy those routers, those devices, they will give you a URL and you connect. There will be user panel and you configure all those stuff there, right? IP address, subnet, etc. Okay. And then there's a simulator there. You can play with it, and this will be in the lab. Okay, and the last part is programming. Okay, so socket programming and this stuff, right? So you need to understand the concepts so that you can program accordingly. It's okay.
Yeah, I just didn't know because I wasn't able to attend the first.
I got it. Okay. Yeah, so you don't have to wait. I see one question asking whether you need to remember the years, etc. Right. So for the history stuff, you don't. We will not test your history, which year, what happened. Okay, these are for you to help you to memorize and get the big picture, because later we will really go down to each individual stuff, right? Like what is TCP, what is router, and once you have this high level idea, then it will be easier for you to understand. We will not test this history. Okay, so this is not a history class. Yeah, it's concept. Okay, yeah.
I have a question. Do we have lab today?
No, we don't have lab for the first week because there's student adding job, right? So we don't want the new students to miss the lab, and some students may drop it. So we will basically we will have the lab next Friday, starting from next Friday. Okay.
Okay.
Yeah, this is also on the announcement, I believe. If you look at the announcement, yeah, again, if you don't get the announcement in no lab today, okay, so if you don't get this is a TA, by the way, right? If you don't get the email notification, just figure out with Ask IT, or you let me know. I can help you connect to them. Okay. Yeah, have a good weekend. So if you have no more question, I will disconnect. Otherwise, you can send me email, okay, or also the TAs. Okay. Thank you. Have a nice weekend. Bye. We will share the video, by the way, later today, okay, once it's uploaded and processed by YouTube.